Okay, welcome everybody to our 12th Solar Climate Intervention Virtual Symposia. We're meeting again after a little bit of a summer break. I'm excited to have two speakers here today. And we'll start as usual. Well, first, as usual, we will have 20 minutes of presentations, and then we'll have 10 minutes of discussion. So please keep yourself muted during the time, and you can always add questions already in the chat while we have the speakers talk, and then have the discussion afterwards. So our first speaker is Ye Tao. He is the founder and executive director from the Mirrors for Earth Energy Rebalancing, or MIR. And today he will talk about from Geo-Experiments to Geoengineering, the journey ahead for energy rebalancing at the Earth's surface. So please, Dr. Tao, share your screen. We already see it. Great. And go ahead. I will remind you 5 minutes before your time is up. So you can then know that you need to wrap up soon. Thank you.
All right, thanks, Simone. I think it's great to have a geoengineering audience for once. And I think in thinking about this talk, it has made me really think about what's are the common challenges for the entire field. And I think it will be an interesting, it's been an interesting process for myself as well. And today I'd like to start by maybe making a few comments or thoughts about what's been pitched as a adaptation mitigation dichotomy or a competition in the climate adaptation or climate change space. So I think the real difference between the two is that in adaptation, we're trying to alleviate the symptoms without really addressing the underlying causes, typically speaking, in the traditional sense. And that in mitigation, we're trying to address one of the direct causes. But I think the differences start to fade once we go beyond these 2 points. So, for example, I think both helping the poor and also trying to undo the damage to the environment from burning fossil fuel are sort of virtual signaling for many of the participants currently. So these are talked about, and there's certainly many small demonstrations of both types of efforts, but we don't really have any significant scaling of either of these. And both are pretty expensive. So if you're trying to build a seawall for a city, for example, it's an overhead for the city's budget. So it's not very feasible or likely to happen in the near future. And it's also very expensive from the mitigation point of view, because if you want to switch from fossil fuel, which is essentially a very cheap form of energy, because you can invest very little energy and get a lot out. So currently, the energy return on investment for fossil fuel is about 30, whereas for renewables, with and without energy storage, it's between about 5 and 15, so it's around 10. So from a physical sense, the price of fossil fuel is just simply cheaper than renewable, and that's hampering truly significant at-scale mitigation. So from an economics perspective, neither of these, neither adaptation nor mitigation in the traditional sense through carbon would likely happen in free market economy. So it's very likely that there would be very limited scaling of either of these before the energy return on investment for fossil fuels falls significantly below their renewable counterparts. But these are the perspective of people in the policy field who are, for example, main players in the current system. But unfortunately, already, many people are being more or less driven out of the economic system by a combination of different stressors. For example, heat, for which many outdoor workers are already paying a hefty price. And there's also people around the world spending abnormal amount of time just to get the basics. For example, drinking water. So there's recent stories of Indian high-tech workers getting out of their office in order to get water. So they're missing their jobs. And right now, 10% of humanity cannot afford to eat 1 meal per day. And the situation is getting worse every year since 2014, when the hunger ratio was about 7%. Now it's at 10%. So these people are already no longer part of the system. So looking into the future, I think there's a urgent need to ensure very basic human necessities for survival, including food, water, and also safe healthing. So we coined the term adaptive mitigation. And it came about because sunlight, as you know, is the source of many energy on planet Earth, including for the ecosystems. And now we're also capturing part of it to run our civilization. So if we can manipulate, optimize, or capture this energy upstream, we in principle have the most leverage or ways to influence downstream processes. So the question really is it possible that in the effort, gigantic effort in trying to maintain human habitat through direct cooling method, can we, as a byproduct, unintentional consequence, also lead to passive cooling of the biosphere and eventually of the whole climate system? So the question is, can we create as a byproduct global level scale cooling on the order of 1 watt per meter squared by simply trying to maintain human habitat, by ensuring fresh water, agricultural productivity, and safe housing? So that is the logic or hypothesis of adaptive mitigation. So let's do a thought experiment and consider the temperature change that will be induced in different subparts of the Earth system. If we take away from them the energy, the solar energy that falls on the built environment on planet Earth, which currently is about 0.54% of the land surface area. Through very simple calculations, because you assume very simply that there's no transfer of heat out of this hypothetical situation of this one particular chosen environment. For the case of, say, fresh water, you can calculate that the daily solar radiation falling on the built environment would cause a temperature change of about 1 degree Celsius. One can do very simple experiments to test the order of magnitude impact. So if one reflects about 60% of the sunlight impinging on these bins, one can reduce temperature by up to 10 degrees Celsius on a daily scale. And averaged over the day, it's about 3 degrees Celsius, 3 to 4 degrees Celsius. And if we scale that by the different coverage ratios and also the ratio of the global average reservoir depth and the bin depth, one finds that if these results were to extrapolate to the global reservoirs, then one expects about half a degree cooling of the global reservoirs on the daily scale. Of course, it's slightly less than the 1 degree because in these small scale cases, there's lateral loss of heat and also there's turbulent heat loss as well. In land systems, for example, in the soil, one can also measure a good fraction of a degree to a couple of degree reduction at 10 to 25 degree centimeter depth. So extrapolated to, again, the global soil, it's again the same factor of 2 for agricultural purposes, that is. Then what about this case that really stands out? The built environment. If we take energy, solar energy out of our built environment, our urban systems, can we alleviate impact such as the urban heat island? Well, we chose to undertake an experiment, and we chose a slum community in Sierra Leone where people are really suffering. Over this very small piece of land measuring about quarter mile by quarter mile, there's about 40,000 people. So the population density is about 1 person for every 3 square meters. Most households live under these corrugated iron sheets, and during the day, it can get really hot in there. Heat is a silent killer, and we still do not understand the full physiology, but it's certainly a very uncomfortable stressor. And a recent paper showed that for older women, starting at 35 degrees Celsius, the body already starts to be unable to compensate for the heat through reduced capability to sweat and also thermoregulate. And by about 40 to 45 degrees Celsius, almost everybody would be unable to cope such heat stress for any extended period of time. We took some measurement in this poor neighborhood and found that during the 3 hottest hours of the day under these roofs, temperatures are already such that most people, well, at least half the time, the people would, every person almost would be suffering from heat stroke if they were to stay inside for an extended period of time. That's why when we visit the neighborhood, we see people more or less hiding in the alleyways in the shade, lying along the road during the hottest hour of the day. They cannot really stay inside. So that's consistent with our physiological understanding. We changed the surface reflective properties of several buildings. For example, A4 and A7 to aluminum-based mirror, and C4 to a white paint. In the case of the mirror, we measured a very significant decrease in roof surface temperature by up to 23 degrees Celsius. And this reduction of roof temperature translates into a reduction of indoor air temperature by between 5 and 7 degrees Celsius. So from a physiological perspective, this intervention was able to change conditions indoors from one that's causing heat stress to one that's now safe, and one where most people can do some moderate activity such as studying and light housework. So we have shown a few examples of how adaptation could be achieved using localized solar radiation management. But calculation also shows that at such small scales, the impact at daily scale for much larger structures that we care about, for example, the global soil where microbes, fungi, and the roots of Amazonian trees grow, would be rather small. But we have to also understand that different structures have different time constants. So for certain structures that respond slowly to the radiated forcing impacts, we can expect that they would potentially be able to accumulate or integrate the impact over time. So there might be the possibility that even small impact could eventually be picked up by these larger physical structures. Moving beyond local adaptation, we really need to be careful because we all know that there may be teleconnection impacts and long-range impacts that's not unintended. And as a step towards that global understanding, we need to start thinking about what are the regional impacts. And to do that, you need to consider the response of clouds, how the turbulent heat would react, and also the instantaneous long wave adjustments, both locally and also in locations where turbulence will carry your cool air patch. So the road ahead, I think, is one of measurement and also computation. I come from an experimental perspective, and that's why I think our contribution could be on the sensor front. And today I will try to discuss some of the challenges that this field as a whole may be having and how we're moving towards resolving some of these challenges. So I think problems that we currently face include poor accuracy of in situ sensors, and also some of them respond very slowly to the actual conditions. We also have a fairly poor spatial coverage by in situ sensors. That has led to an over-reliance on the use of remote sensing data for computational purposes. So right now, I think many colleagues in computation and model building use reanalysis data. One example includes a recent paper that uses a artificial intelligence core to get at subgrid parameters. But this component still takes ERA5 data as input. So the predictions can only be as good as the quality of such reanalysis data. Unfortunately, it's known that such reanalysis data still has significant bias and also random errors. And both comparison with satellite-derived data and in situ measurements show that we have between 1, 2, sometimes up to 3 degrees Celsius differences, disagreements for such simple parameters as air temperature at 2-meter height. We also confirmed that satellite measurements carry a significantly larger error compared to in situ measurements in our Trapped-Time experiment. But these in situ measurements themselves, because they're taken by physical sensors, have themselves also different biases and noise sources. So we'll talk about those. To do experiments, people typically buy or purchase these research-grade weather stations. And you may also, as a citizen scientist, choose to buy something cheaper at the expense of higher inaccuracy, up to 1 degree Celsius for air temperature measurements. And these instruments are not very cheap either. So they're in the tens of thousands of dollars, or at least almost up to $1,000 for these cheaper commercial variants.
You have about 5 more.
Okay, thank you. So in order to make them more affordable, we have undertaken some sensor development efforts. So for example, these optimized sensor type 1, 2, 3 that you see here bunched very tightly together, they achieve fairly good precision and agreement with each other. And compared to the commercial sensor, we can see a very distinct time lag of the commercial sensor that we hypothesize to be much larger thermal mass for the temperature sensing element. And the time lag can be up to 5 minutes to 10 minutes, which can be another source of uncertainty in existing measurements. And our sensor can also exhibit much faster time domain response rates. So that can, in the future, aid in capturing important dynamics on the minute, second to minute scale. And another challenge for the measurement community are these is the measurement of radiation, which currently carry about 5 to 10% uncertainty. So here are some examples of uncertainty in shortwave radiation versus reanalysis, and the long-wave radiation versus reanalysis. And this problem doesn't seem easy to solve because the technical papers developing these potentiometers really report that even the authors don't know why sometimes the long-wave sensors really disagree with each other. They have some hypotheses. Part of it is due to sunlight leakage, but there are also occasions where in the absence of solar radiation, they still have huge disagreements. And with very careful calibration efforts, you can probably achieve 5 watt per meter squared of measurement uncertainty, which is absolutely huge when we're talking about, in the end, working with just single-digit watt per meter squared overall energy balancing interventions. So the final point I would make is that currently we don't have very good spatial coverage of sensors on planet Earth. About 1 pixel for the general circulation models. And that has led to many problems, such as disagreement between model prediction of cloud response to deforestation. So for example, computations suggest that cloud should increase when you cut trees in Siberia, but the observation shows the opposite. When you cut trees, cloud decreases there. And the opposite effect is observed in the tropics. So this could be attributed to cloud processes being at much smaller spatial scale, so on the order of a few kilometers. But even dispersing sensors on 1 kilometer scale may not be sufficient. So in our next phase of experiment, we found that if you place sensors at high spatial density, like 10, 20 meters spatial density separation, you can still, in the end, measure highly heterogeneous temperature fields. So it becomes very questionable how and at what frequency or sampling spatial frequency you really need and how to really obtain accurate and reliable and representative in situ temperature data. So the challenge is huge. We need to increase the number of sensors by orders of magnitude. And hopefully we're moving towards that. And in our spare time, we're scaling up our project, using low tech, such as plastic bottles, to make furnitures and also cooling infrastructure. And we're currently building a public shading structure that measures 280 square meters, that offsets about thermally 28 tons of CO2. And that's equivalent to the emissions by the team members in Freetown over their lifetime, because the per capita emission there is only 0.14 ton per year. So with that, I'd like to thank our Freetown team, the Pune team in India, and also other support staff and team around the world and in the United States. Thank you.
Thank you very much for the very interesting talk. We go over to the discussion now. If you have any questions, please put them in the chat or just raise your hand, and then you can unmute yourself and ask the question. Yeah, so I think this is very interesting, focusing on local mitigation, local adaptation to cool certain areas. And it seems like you already did some tests that it actually really matters for a small area. But how is that? Is that something you're planning to also expand further? I mean, if you think about various communities that suffer really the heating in those circumstances.
Yeah, so far we have only implemented the project on single building scale. So we have impacted maybe about tens of people, so about 50 people. So our next phase is to ask the question, what happens if you made albedo enhancement over entire neighborhoods? Near the end, I was showing this highly heterogeneous temperature field. So that's the background temperature measurement in preparation for a hectare scale, community scale albedo intervention trial in the next two years. So we plan to do that over several phases, 3 phases. In the first phase, it would only be half a hectare, so roughly 70 by 70 meters square. And beyond that, I think we still have to think about how to get the logistics done. So we're just busy doing the architectural design and also prototyping, demonstration for safety for the hectare scale trial.
All right, great. Is there anybody else who wants to ask a question? There is one from Hongwei. Do you want to unmute yourself and ask the question?
Yeah, I can. Can you hear me?
Yes.
Cool. Yeah, very nice talk. Yeah, my question is about, can you say a little bit more about the local albedo enhancement you mentioned? Like, if you put some, is there any popular material or like something what you did to increase albedo? Thank you.
So the most mature method in the field, many people have heard about, is white paint. Traditionally, it's been the easiest to put on the roofs. So we also had one building which was done that way. But now we're currently exploring multiple material systems and multiple application methods that include sticking on the metal layer of the roof, for example, or free suspension of reflective sheeting over the structure we're trying to cool. We're also in collaboration with multiple companies and research groups that will together join us actually this fall to expand on the single building project. In the field of material science in recent years, there has been a very rapid development of what's called daytime passive cooling materials. So these are highly reflective paint, fabrics, or films that under direct solar radiation not only doesn't heat up, but actually cools down to below ambient air temperature. And they do that by being able to emit thermal radiation between 8 and 13 microns. So it's in the atmospheric transparency band. So they're able to bypass the greenhouse gas effect. We have 3 groups now likely 4 groups confirmed that will join us with their different fabrics, paints, and additives in the next 2-3 months. So it's a really fast-moving space in the startup and research space.
Cool, thank you.
Right, and is this also internationally? You're working internationally with different groups, also here in the US, in different places?
Yes, yes. So the groups are from the US, France, and China. The material makers.
Yeah, yeah.
Oh, and
Great.
also Belgium, sorry.
All right. Okay, there's one more question. Yang, please unmute.
Hey, thank you. Yeah, I have a question regarding to the line you draw between adaptation versus mitigation. So the good examples you have shown at the neighborhood scale is certainly a good way to for local resident to adapt. But also you mentioned effectively they are also reducing the carbon emission. So I wonder if that quantification can be credible or verified by third party for local people to claim credits as an additional financial incentive to scale up the process. And also in the long vision, how do you, in terms of scaling up, where did you draw the line of global mitigation, such as massive deployment of murals or other reflective material over, say, desert or open space? I think that fall into a different realm of discussion. So I want to get some thoughts from you.
Okay, excellent question. So first part is about how to quantify or make equivalency between albedo enhancements or other type of radiative cooling and carbon credits. We have this impression that somehow carbon credit field is mature and very, very precise. That's cannot be further from the truth. Many carbon credit projects cannot be carefully or precisely verified. And there's a huge uncertainties in the assessment of, say, for example, above and below ground biomass. And there's also a lack of, policy enforcement to really make sure people are looking carefully and accounting for all the different complementary pathways. And I don't think people are thinking about when you capture carbon, for instance, you decrease by a little bit atmospheric carbon content. That has the impact of virtually slowing down carbon capture by the ocean. So there's, for example, an off-gassing mechanism from the ocean, which doesn't seem to be incorporated into the carbon market. So my first point is the carbon accounting itself is not credible or precise. Now back to the albedo, we face the same problem exactly. While you can very precisely quantify local cooling by deploying large amounts, high density of local sensors, once the heat or the cold gets out there in turbulence, in radiation, it's very challenging to account for how they travel. So before we can have a very robust accounting method, I think we really need to be working on the sensor systems. I mentioned that even radiometers are off by 10 watts per meter squared. For example, how are you even going to measure, say, the impact of your marine cloud brightening experiments? What's the IR impact of that? If you cannot measure to, say, within well below 1 watt per meter squared precision and accuracy and reproducibility. But people are working on trying to make this equivalency. There are multiple groups working on that. We tried a little bit, but that we, as experimentalists, quickly came to the conclusion that the science, the infrastructure, is simply not there for you to make a very precise and rigorous quantification. You can do, within factor of 2 assessment. We can probably do better than carbon already, but I don't think that's something that we have the time to invest as a group. There are other groups with comparable or better expertise to address those issues. So your second question, if I may remember well, is about where do you draw the line between adaptation and mitigation impact? I think hand-wavy number would be on the order of 0.2 or 0.3 watt per meter squared globally averaged cooling power. The reason I give this number is because historically, land use changes has already induced that order of magnitude in cooling. And apparently there hasn't been dramatic changes in global circulation patterns and impacts. But beyond that, we're reaching towards current greenhouse gas mediated radiative forcing. We need to be careful. So the line, I think, is around 0.3, which is halfway in logarithm scale between historical precedents and also the eventual targets.
Yeah, okay, great. We have one more, if it's very quick, from Gregory, else please put it in the chat. Can you ask a quick question?
Yes, thank you. This is an excellent talk. I'm very impressed. But it seems to me that, I mean, we're in an emergency now. 1.4 is already catastrophic. And you should be rolling out right now as you test. And I would compare it to the vaccine process of massive testing, during which time millions died or hundreds of thousands, whatever. It's in an emergency, you relax the standards, even as you attempt to upgrade the measurements and the precision of the scientific analysis. So you should be rolling out as fast as you can, while you're also doing all these increased measurements. That's what I think.
Okay, thanks for the comment. I think I agree that we can also work on the scaling part, because with any reasonable or under any reasonable scenario, I don't think we can scale beyond the 0.3 watt per meter square globally average cooling within the next years, where I believe many of the measurement techniques and new sensors we have plans to develop and implement would become much more mature to also contribute to other fields of solar radiation management science and testing.
All right, well, thank you again for the great discussion and the talk. I would like to move on now to our second speaker. And our second speaker is Linus Boselius from the University College London in the UK. And he has been working with Peter Irvin. And today he will present on peak shaving with solar radiation management with shortened global temperature overshoot. Please share your screen, and then I'll let you go. We'll still want this in full screen if possible.
Okay, like this?
Yeah, not yet. Yeah, now we'll see it. Great.
Oh.
Okay, please go ahead. Thank you. And I let you know 5 minutes before the end. Yeah.
Great. Thank you so much. Hi, everyone. Thanks for having me. I'm Linus. I recently completed a master's and research internship at UCL. The project I was working on was eventually titled Peak Shaving with Solar Radiation Management Would Shorten Global Temperature Overshoot. The project was supervised by Dr. Peter Irvine with help from Alistair Duffy. So thanks to both of them for their work on this project. And we have a paper that's currently under review at Earth's Future. So hopefully our findings will be published soon. Excuse me. Sorry, let me move this out the way. There we go. Okay, so to introduce peak shaving, I have our classic napkin diagram here. If we imagine the y-axis as global temperatures, in green we then have a global temperature overshoot, where a temperature target, for example here, is exceeded and then later recovered here, thanks to aggressive emissions reductions and large-scale carbon dioxide removal, CDR. So such a scenario could be adapted with the implementation of solar radiation management, or SRM, to give us this peak shaving scenario here in blue. However, when we run peak shaving scenarios in climate models, they don't quite come out looking like this, and we instead see some overshoot shortening, which I'll explain now. So here we have the model output for one model run, where we feed in an emission scenario that produces this overshoot here, exceeding our threshold temperature, in this case 2 degrees here, and recovering it centuries later here. So if we take the same emission scenario and now apply peak shaving with SRM, our results look like this. So SRM begins as the threshold temperature would have been exceeded, and it maintains that target temperature throughout the overshoot until it is no longer required here. And this occurs several decades before the target temperature would have been recovered without peak shaving, which is what we are terming overshoot shortening. So overshoot shortening can be quantified by the difference between when the SRM can be ended and when the threshold temperature would have been recovered without SRM, as marked by these two dotted lines here. So overshoot shortening has been exhibited but not addressed in the results of previous literature. So this project was looking to provide an initial quantification of the overshoot shortening effect, as well as explore some of the mechanisms behind it. So onto our methods. We use the finite amplitude impulse response, or FAIR model, which is a reduced complexity climate model that works to emulate the behavior of more complex system models. We used a calibrated constrained ensemble of model parameters, and our study used an ensemble with 603 members. And we created this emission scenario to generate our overshoot. So we have our annual CO2 emissions here that follows the historic emissions, and then SSP2 4.5 as a moderate scenario up to 2100 as far as it's defined. And then we followed our adjusted extension rather than the classic Meinshausen et al. 2020 extension out to 2500. Our extension continues the trend of SSP2 4.5 beyond 2100, reaching net zero in 2130, and continuing into net negative emissions to generate that overshoot, reaching minus 10 gigatons of carbon dioxide per year in 2155, and maintaining that until 2500. SRM was implemented in our model through the volcanic forcing input, which serves as an analog for stratospheric aerosol injection. And we used a proportional integral derivative controller, which is a feedback controller to determine the year-by-year amount of SRM required to maintain the target temperature throughout the overshoot. Okay, so onto some results here we have for quantifying the overshoot shortening. On the right here, we have the figure you saw before, just so you can visualize overshoot shortening. And on the left, we have the percentage overshoot shortening against the original overshoot duration for each ensemble member in our study. We can see how the, for every member of the ensemble had its overshoot shortened as a result of peak shaving with SRM. And that this shortening ranged from a 5% shortening up to approximately a 20% shortening. And that increase went from the original overshoot durations of 60 to 300 years, after which they appear to stabilize at approximately 20%. So although there's a lot of spread about this trend here, we can see that the overshoot shortening is substantial from our study. So on to some mechanisms, then what might be driving this effect. We first investigated the carbon cycle response to peak shaving. So most climate models agree that there is a positive carbon climate feedback. So high temperatures reduce the efficiency of carbon sinks, thereby increasing atmospheric carbon. For example, higher temperatures increase the rate of heterotrophic respiration or decomposition, which decreases soil carbon retention. Higher temperatures also increase the rate of permafrost thaw, for example, which also increases atmospheric CO2 or carbon. So the idea here is that the avoided temperature increases under a peak shaving scenario would decrease atmospheric carbon, driving overshoot shortening. So the results on this from our study can be summarized by this figure here, where we have the atmospheric CO2 concentrations for each scenario. We can see from the implementation, or after the implementation of SRM here, the peak shaving scenario remains marginally below the overshoot scenario in terms of atmospheric CO2. And the peak mean difference in CO2 concentrations are shown, well, we can see the peak mean difference in CO2 concentrations here in green at approximately 2.5 parts per million. So this isn't a very significant difference between the two scenarios, and that kind of concentration difference roughly corresponds to a temperature of less than 0.01 degrees of difference. So this, along with our other analysis, shows us that the carbon cycle response to peak shaving was unlikely, what was not driving the overshoot shortening in our study. So next, we looked at the ocean response. The ocean response to peak shaving. So as we know, the ocean regulates surface temperatures. So as surface temperatures increase, the ocean takes on a lot of heat as well as carbon, inhibiting those surface temperature increases. And the idea here is that the avoided ocean warming under the peak shaving scenario would strengthen the surface temperature response to negative emissions. And I'll explain what I mean there with results from our study. So here we have the temperature response, the temperature responses for each model layer in FAIR. So we have the surface, the upper ocean, and the deep ocean. Here I've got just for our overshoot, not the peak shaving scenario. So we can see how the ocean temperatures follow a similar trend to the surface, but with diminished and delayed temperature responses. But we can also see that the ocean temperatures do reach a peak and then decline, meaning that the ocean changes from a heat sink to a heat source as it loses heat to the surface. And this, sorry, excuse me. So yeah, so if we then show the peak shaving scenario here, we can see that the surface temperatures are maintained at that threshold temperature of 2 degrees and then decline following surface temperature declines. Along with the overshoot temperature declines. And then we also see that the effects of peak shaving extend beyond the surface, affecting ocean temperatures as well. As we can see, the red lines remain below the blue lines. So this means that the oceans are cooler comparatively in the peak shaving scenario relative to the overshoot scenario. And the cooler ocean would be, a cooler ocean would be a more effective heat sink and a less effective heat source, meaning that the surface temperature response to negative emissions, to net negative emissions, would be strengthened. And that would lead to expedited cooling, which we find is driving the overshoot shortening in our study. So onto the implications and limitations of our study. So most obviously, overshoot shortening would reduce the duration of SRM deployment for peak shaving. In our study, this was by 40 years for the median overshoot. So this is significant because of the many costs and challenges associated with SRM deployment, as well as the side effects. Also, the second major implication of this study is that it would lighten the burden of carbon dioxide removal efforts to recover the threshold temperature in an overshoot scenario. So in our study, the cumulative net negative emissions were reduced by 27% in the peak shaving scenario compared to the overshoot scenario. And similarly, this is significant because of the many and large challenges of large-scale CDR efforts. For example, direct air carbon capture and storage faces very high costs, and bioenergy with carbon capture and storage has a very high environmental footprint. And this would reduce the burden of CDR if the goal is to recover the threshold temperature in an overshoot scenario. So some limitations of this study. One major limitation is the simplicity of the FAIR model. It's a reduced complexity climate model, as I've mentioned, but it's also on the simpler end of reduced complexity models. It's highly parameterized and works off globally average systems. So many responses or many processes aren't necessarily accurately or very well captured by the FAIR model. For example, it lacks a permafrost component, so the carbon cycle response to peak shaving may be underestimated or is likely to be underestimated in our study. And the simple representation of the ocean in this model, just having two layers, will of course miss out on some of the complexities related to changes in ocean circulation and so on following peak shaving or in response to peak shaving. So it would be great to see a similar study done in other climate models, such as more complex set of system models or other reduced complexity models as well, to compare results. This study was also somewhat limited by the lack of alternative scenarios. So we just used the one emission scenario in our study. And although the underlying physical mechanisms mean that we expect similar results to happen under other emission scenarios, it would be great, of course, to compare with other emission scenarios and perhaps other threshold temperatures and different methods of peak shaving. So some takeaways from this talk. SRM for peak shaving can be ended before the target temperature would have been recovered without it. So this is what we're terming overshoot shortening, and is illustrated by this figure on the right here. The percentage shortening increases with overshoot duration up to approximately 20% for multi-century overshoots. And the shortening is mainly driven by avoided ocean warming in our study, as opposed to the carbon cycle response to peak shaving. So that's all. Thanks.
Thank you very much. And also very nice to stay on time and end a little early, so we have a little bit more time for the discussion. Yeah, very interesting discussion. Do we have questions? I see already one there. Tyler, please go ahead and unmute.
Thanks, Simone. Thanks, Linus. Sorry if I missed this at the start. Could you describe the SRM deployment pathway? And do you think that might matter? Referring back to the original, your final slide there, the graph. Is it a rapid ramp up and a rapid ramp down, or do you think that would matter in this result?
Yeah, sure. I can. I actually have a figure for that here, I think. I don't actually, sorry. So yeah, so from this graph, the SRM starts when the 2 degrees threshold is exceeded, and that was in our study around 2059, I think, was the median time. So in a reasonable amount of time, according to some scientists. And yeah, it basically ramps up as the temperature ramps up. So as it's having to offset larger and larger temperatures, it ramps up as well. So the median peak temperature in the overshoot for our study was 2.7 degrees. So it was overshooting. So the temperature overshoot of 0.7 degrees was offset by SRM in our study. So it's not a huge amount relative to the potential, but yeah, so the forcing graph kind of mirrors that overshoot. So it ramps up and then ramps down again until it's no longer required anymore.
All right, thank you. Let's go to the next question. Andrew Lockley, do you want to ask a question?
Yeah, I did read the abstract for this, and I also listened to the talk, and I'm obviously missing something really basic because I don't get the difference between the overshoot and the peak shaving scenarios. So if you could explain to me, like I'm 5, what I don't understand, help me understand.
Yeah, sure. I can have another go. So we can perhaps illustrate it with this here. So they're basically completely separate situations in a sense. So the overshoot scenario, we don't use any SRM, but we just have aggressive emissions reductions and large-scale carbon dioxide removal. So temperatures increase.
Oh, right. Okay. So it's overshoot. It's not, sorry, the misunderstanding I had is I thought you were using SRM in response to the overshoot, and I couldn't understand what the difference between. So basically, you're comparing an SRM scenario to a no SRM scenario in a condition of overshoot, right? Okay, that's fine. Yeah, I get it now. Yeah, cheers. Apologies.
All good. Perfect.
All right, great. Anybody has their hands up right now? I don't see it, but there is some comments in the chat. Gregory is asking about defining the upper and deeper ocean, and also if FAIR is an emulator or a numerical simulation.
Yeah, sure. I can speak a bit about that. So FAIR has 3 layers, and they're essentially just defined in terms of heat transfers and heat transfer coefficients. And the model can here's a schematic of the model, so all its components here, and it can actually be summarized by, or it essentially works off of 6 equations that feed into each other, and that's shown here. So it is a model rather than an emulator, but it does work to emulate more complex models. But yeah, that's a little bit about the FAIR model and their papers. You can see here in my footnotes that you can read more about it, and a website where this was taken from, which should be quite easy to find here. Yeah, fairmodel.net.
Yeah, I can see that there is some major uncertainty in the ocean response. Of course, as you're saying, it would be really interesting to perform these more extensive simulations with global models. And I think, Rob Wood, you also have a comment to this. Do you want to raise your...
Yeah, happy to unmute. Hold on. Yeah, it's just it just struck me since you were showing out to like very interesting result, by the way, out to 2500 or beyond. If you take the power law, you know, how much power we're using, and just extrapolate that, it doesn't take that long before you find that we're using all the energy from the sun, or the energy intercepted by the Earth, not all the energy from the sun, sorry. And then you get to the point where the heat from direct power use, right, is bigger than the heat input from CO2 and greenhouse gases. So I just wondered if you thought about that. I just kind of, it's not really science fiction. It's not that far away if you're really thinking 2500.
Yeah, of course, 2500 is a long time frame to be working with, of course. And we could also do the study on a shorter time frame, but that would of course need much more CDR much sooner and much more SRM. So given we're using these technologies in our model, we opted to go for more moderate pathways where possible, and that meant expanding over a longer time frame in our study. But yeah, it would be interesting to see results from shorter time frames as well on this topic.
I'm just curious if anybody's actually thinking about the power use. Is the power use strictly, is it continuing, does it continue to go up, in these models? I'm thinking more like the more sophisticated, where they use the energy, consumption and economy, econometric models. Does the power consumption keep going up as the same as Moore's law is today? Like similar to that, the rate, do we know? Or do they kind of pull down the power consumption? I'm talking about like total energy use, not even renewables produce this heat, right?
Yeah, I guess it doesn't exactly feature in the model we're using, but I think there'll be stuff on that, for example, in Mine's House and that's our paper here, and in that paper they're thinking about how to extend these SSP models out to such an extended time frame, and they made some different decisions to us in our model here. But yeah, I'm not sure, basically.
Yeah. Anyway, thanks. Yeah, thank you.
All right. Well, if there are no more questions, I think, although there is one, I think there's one more question by Erp Simmons. Do you want to unmute yourself?
I think I've read the question here. If not, so it's hard to imagine a society that is stable enough to carry out effective SRM in 35 years. And yes, that's of course true that SRM would require a lot's got to happen between now and SRM deployment. And while it's hard to work out, to quantify how soon that can happen, an expert survey that was conducted a couple of years ago, I think it was in a Sovacool paper, I might need to double check that, and the median year of when they thought SRM or SAI deployment could potentially be deployed was 2040. And while that is very soon, we were kind of working off of that as at least that is potentially feasible. But of course, there remains a lot in between now and any potential SRM deployment. Yeah.
Right, yeah, there's a lot of uncertainty and questions about that. All right, well, thanks again to both of the speakers. So we now conclude our symposium, and I hope I see you next time. If anybody would like to present at our symposium, please send us an email, me or Matthew, and so we can put you on the schedule. All right, and with that, have a good rest of your day and a good weekend. Bye. Thank you.
Thank you.
Bye-bye.